questions. So A is the start of this interval over here. So A is the starting time in days, right? So we're going to have some moments, right? It's a big moment, right? So this is about focusing on one moment, and A is the starting time in days for the moment. And then that's what you select here by A. So right now A is, let's do it over here. Move it a little bit further back. That's good. Right now A is 1.6, so the moment starts at 1.6. And then N will show the time in days increasing through the moment. And as it does that, then over here, this is like supposed to be showing the accumulation at that rate in that moment. So again, starting at 1.6. Now we're disregarding the previous amount accumulated. So every moment, no matter where you start the moment, the amount accumulated from before is going to be 0.3. Right? So even if we start the moment back here, it's still starting. So now the moment starts at 0.55. The amount of oil accumulated to that point is still 0.3. So we're just disregarding that part of it for now. Okay, but given a moment and you're increasing the time and days through that moment, then you watch the volume of oil go up at that rate, at that constant rate, in the moment. And then you're going to fill in symbolism, expressions, letters, expressions, whatever, for all those question marks, so that when you turn in yours, those are not going to be question marks, but those are all going to have appropriate symbolism for all those question marks. Okay, so questions?
Were we supposed to have that rate?
Yeah, I'll give you that rate. Okay, write it down. Or it'll be on the video. I'm recording. So it'll be on the video, or you can write it down. But this is the rate function. 20 cosine, but I want you to get the mathematics right, first and foremost. Now, in this project, the question marks are very important. Okay, so we want to get those. Other questions?
How do we do 2 screens like that?
Okay, so second screen. We haven't done that before? Yeah, use apostrophes on your Y's and X's. So if I come here and I do Y apostrophe equals X apostrophe, this is not derivative, okay? This is not Y prime and X prime. This is GC's convention for graphing in a second screen. So if I do that, it will graph the line Y equals X on the right-hand screen. Don't do that in your project, right? I'm just showing you. But when you graph something, every Y and every X in that equation, even like if I'm gonna like restrict it, say I restrict it from 0 to 2.5. It doesn't work. It's got to be every single X and Y. So I got to put an X even on that restriction, and then it'll work. So in that line that you're graphing on the right-hand pane, every single Y and X has to have an apostrophe. And then you get points over there. So you know how you can just graph a point with Control 2, right? I'm not saying you'll need to do this, but this isn't, while we're talking about it, this is important. So like the point 1, 10. So that'll graph the point 1, 10 over here on the left. If you need to plot an individual point on the right, then you need to do X apostrophe Y apostrophe equals, and then I can do 1, 10. And that'll plot it on the right. So you need this extra how big is my moment, right? What does the value of n represent? You know, think. What is the value of n representing here? And so, is this a appropriate use of this or not? Okay, so we've worked a lot on what's happening over here, right? We've spent a lot of time understanding and watching a quantity accumulate. This is a quantity accumulate at a constant rate of change, and we've gone over, we've unpacked that, and unfolded that many times. So you have to decide: does the morph operator help you with that? That's what this is really all about. Is this thing over here? Okay, other questions? Good to keep working on it? Any questions? Anybody? Last chance? Okay. So let's press on with our endeavor here. What is our endeavor? What's the big picture of what we're doing right now? So there's going to be lots of details and math and equations and variables and symbolism, but it's all for naught if we don't know the big picture of what we're doing. Why are we doing it?
To find accumulation at this moment.
Okay, so are you responding versus about this project?
Oh, okay.
Yeah, I'm just saying in class in general. Here's our oil, right? And what is this about the oil? The rate of change function, right? And what was this? How much oil ends up in the ocean, right? Relevant question, right? Calculus is about modeling the real world. It's relevant, right? So given this rate of change function, this function then is how much oil is in the ocean on any given day. How much is expelled in total? So we would want to know that. Okay, so the problem we're working on is, you know how fast the quantity is changing at every moment, and you want to know how much you have at every moment, okay? This has to be in the forefront as we're getting into because today we're going to get into some nitty-gritty details, okay? It's going to be like some harder mathematics. But it's, like I said, it's really kind of worthless if we don't understand the big picture and our goal, right? So our goal is, we've got this rate of change function. We want to get the accumulation function to know how much of the stuff we have at any value of, in this case, days, but in any value of the independent variable. Okay, so what does that look like? The key to getting said accumulation function from rate of change function is what? So given the rate, this is it. This is the key. Well, how is this the key to getting from how fast something's changing every moment to how much of it you have? Why is dv equals mdt like the whole ball of x here? Or like at the core of it?
So if you know the rate of which something's
And what's the rate?
would be m.
M, okay. So you know m. Then what?
Multiplied by, I guess, changes in x.
Right?
But in this case, is it small changes in x?
Okay.
That would give you the changes of v
Mm-hmm.
starting from some point or 0.
Okay, so given any constant rate, we can calculate a little bit of accumulation, right? How much, a little change in volume. And then how does that help us with the goal? Yeah? Right, so if we've got little bits of accumulation, then we just keep a running total, right? We just keep a running total of those bits of accumulation, and that creates an accumulation function. All right, so, and that's over here, right? That's over here. If we have little bits of accumulation, then we just keep adding to what we had before, and then we get the new amount. So this is, we're talking big picture here, but big picture is really important. It's not about memorizing these little mathematical things that we're going to do, because we're going to do a lot of stuff, but it's always keeping in mind that this is, we're going to start with a rate. That's going to give us a little change in our quantity, and we're going to keep a running total by continually adding it to everything we had before. Make sense? Okay, so I'm going to go up there. This one. So I have a new context now. So this is a rocket basketball. I've never seen one, but there it is. So it's a basketball that's rocket powered. Okay. And so over here, I'm showing the velocity in meters per second and time. So what kind of function is that I'm showing you for the basketball? Is that how high it is? Rate of change, right? Rate of change of height, right? So this velocity, since it's going straight up, it ends up being rate of change of height. All right? And this goes along with what we're saying, that we know how fast something is changing every moment. So we know how fast the height is changing at every moment. Okay? So we want to know how much of it we have. What are we going to do to make progress towards figuring out the height at any moment given this rate of change function? What do we need to do first? What's that? Okay, so we did that. That's the first thing we did with it. Well, so we picked a really small moment and we considered a constant rate. But then we said we got that all done. We got the accumulation in that small moment. But then we said this isn't very efficient, right? Because we'd have to do that same thing for every single moment. So what did we do? What did we do next then?
Approximate.
What's it?
Wouldn't you approximate, like, well, by segmenting this function into like dx's?
Okay, delta x's.
Okay. And from there, like, you just get, or you use the rate from the starting point of each delta x.
Good. Okay. So in each delta x, what kind of rate of change will we have then?
Well, you'd have different ones, but they'd be increasing in this case.
In each delta x. In each delta x, what kind of rate would you have? It would be constant, right? In each one. That's the key, right? So yeah, they change from one to the next, but in a particular moment, we need, so we're going to do big moments, right? So not small moments, we're going to do big moments, and in each big moment, we're going to have constant rate of change, right? So first I'm going to do moments of 0.9 seconds. So I'm going to call that delta t. Is delta t variable or parameter? Right, because it's not going to change. So what would the approximate rate function look like? Can you imagine that? If I use moments of 0.9 seconds, and then what? I'm going to take the rate from the beginning of each moment, and that'll be the constant rate for the whole moment. So that we did this with the oil slick, right? And so now, notice what I got over here. Tell me about this function over here. What's that? Accumulated height, good. Exact or approximate? Why approximate?
Because you still have like some straight edges in there. So
It must, if it has straight edges, it must be based on the exact rate of change or the approximate rate of change. Yeah, so if it's piecewise linear, like the one we built at the end of class last time, it must be based on constant rates or this new function, right? So now we got two rate functions, right? We got two rate functions over here. I got my original velocity function. That's the curve. That's like the true rate of change. And then I have a new, so maybe this is like R sub h. And then now I have a new rate function, right? That's approximate and made up of steps, constant rates. Why do I want that? I'm going to call that R. Why do I want that? If I have this perfect rate function, why do I want this one that's quite imperfect, right? It's kind of butchered it. Why do I want that rate function? Call that just R. Melissa, why do I want that rate function that's now doesn't have it's not exact, right? It's approximate and it's not very good at all. It's not a good approximation. Why do I want that?
Start developing accumulation.
Okay, and what is starting developing accumulation? What is it that I'm going to get that's going to start developing accumulation?
You're gonna get your dy
Right. DH. DH equals,
and
right?
times
DT. See, so he said it's easier. It's easier. It's not that it's easier. It's possible, right? It's possible to now get some little changes in accumulation if I have a constant rate. This is for constant rate of change. This thing that we've been working on all semester. This doesn't work unless we do a super small moment and assume a constant rate, but we know that's not efficient, right? We'd have to do that a zillion times. So with a continually changing rate, it's kind of like impossible to model what the accumulation is, because as soon as you have a change in time, the rate's different. So we need this like pretend rate function of constant rates so that we can apply this, right? Because this is for a constant rate of change, gets us dH. All right, what is our delta t? Here, 0.9, right? I'm clicking, but it's not going on. What's happening here? I don't understand. Oh, nothing's working. Oh, that's why. I was in the pen. Let's try again. Okay, whatever. Here we are. Okay, so I want to, so this is what we said. We said the actual rate function is R sub h, or v. Okay, but then we're going to generate this approximate rate function, or R. And we're going to skip this. So we did this before, right? We did this where we built up the approximate rate function. We did this last time, remember? And then from those, and we used what? We used the exact rate at the start of every interval, and that becomes the approximate rate for the whole interval. So the black one, okay? And then we built up, for the oil slick, we built up approximate accumulation. So we took, say, all the accumulation from before, plus the rate in the new interval, times dt in the new interval, right? This is dt. So what is this? Previous accumulation plus the new change, dH. And so we did, this is exactly what we did for the that's exactly what we did for the oil rate. So we've done that before. So now what is our goal? Our goal is this accumulation function, how much we have at every moment. What we're going to do next is we want to write this. So what would this be like if I had, say, 100 moments? You guys are talking about making the moments smaller. Yeah, we're going to do that eventually. So when you make the moments smaller, say you had 100 or 1,000 moments, then what will this A function look like? What's that? Okay, yeah, so that's what the graph will look curved, right? But then what will the actual function look like, this piecewise function? If I have like 100 or 1,000 moments. Very long, right? You're going to need a line for every moment. So as we have more and more smaller moments, we don't like this, right? So what's our goal? Our goal is we want to write this in one line instead of one line for every moment. We just want one line period for every, that'll give us the accumulation through all the moments. So this is where it gets harder. So this is where the math gets harder, but we can do it. We got the tools. You stay with me. Have your thinking caps on. We can do it, and then review the video as you need to. Okay, so this is our goal. We want to write this in one line rather than having a separate linear function for every moment. Excited? This is cool. Cool stuff. Okay, here we go. But, you know, it's more challenging. All right. So we're kind of gonna change gears again. Okay, so we're gonna like start over and like recreate the wheel again. So now here we are at 5 seconds. I paused life here at time is 5 seconds. Do you see that? So instead of doing like A of 5 in that previous, like, so what is the approximate, how would you find the approximate accumulation at 5 seconds? How would we get the accumulated height, this height right here, at 5 seconds? What would we have to do?
So you insert 5
Yep.
into that T.
That's right.
So you get
So we're,
difference of the difference, right? Or just like the delta x out of that.
what would happen if you put 5 into this function? We want A of 5, right? What would happen? What would it do? It would start here, right? And to put the 5 in here, it would take the rate at 5. And what's the rate at 5? Tell me what the rate at 5 is. Good. It's the v of 4.5. Everyone see that? So I put v of 4.5, or the rate, the actual velocity at the start of the interval, and then times what? What's the change in x or change in t? Would be 0.5. And then it would add it to. And how would it get that? It would have to take 4.5 and plug it into this one. And to get that, it would have to take 3.6 and plug it into this one, etc. Okay, and that, what would that give you then? It would give you, if you put 5 into this, it would total up. It would total up all the changes, right? And give you that height right there. That would be A of 5. Okay, so if we want a one-line accumulation function, we don't want it to look like this. We don't want it to have to keep going back to the previous line. We want to just write a calculation for A of 5 in one line. So, can we do that? We should be able to do that. Just follow the math. And what would that entail? So now I just want to come up with A of 5 just manually, without the function, knowing what's going on here, knowing that I had this exact rate function of t to this actually is t to the 1.3, and we created this constant rate function by taking the actual speed at the beginning of every interval. How do we get accumulation from rate? How do we get accumulation from rate? Today's the day. Today's the day. It's going to stick. How do we get accumulation from rate? Multiply what? What? Constant rate times change in time. This is how we get accumulation from rate. We know how fast something is changing every moment. We want to know how much we have. So given the rate, over a constant rate over an interval in the independent, multiply and you get the corresponding change in dependent. So what is the change in height in the fourth interval? I'm not looking for a numerical answer. Just an expression that represents how much the height changed in the fourth interval. Veronica, what is it? R sub h of 4.5? Is that the rate in the fourth interval? 2.7? Okay. 0.5? I'm asking about in the fourth interval. In the fourth interval. So times. So here's the first interval, second interval, third interval, fourth interval.
T minus 3
No, so the fourth interval is at this constant rate for what change in time? I want the change for the whole fourth interval. So what's the change in time across the fourth interval? 0.9. How am I going to get now? How am I going to get the rate in that? So you see what happened? Right. So this is the fourth interval. It's a constant rate the whole way. Your change in time is 0.9, and the rate is. And what is RH of 2.7? I actually want to get a number here. Yeah, 2.7 to the 1.3. So it has that constant rate for the whole fourth interval, which is a duration of 0.9. So that's how much the height changed in the fourth interval. I'm asking for how much did the height change starting from time 0 up to time 5. Now can you do it? How would you do that, right? So you got the amount of change in the. Okay, so what's that right there? So I want the height at 5. So I want the accumulated height starting from 0 all the way to 5. So what that's going to entail. This is just a slice in the middle, right? This is just a little change in height kind of in the middle of all of that. So what's the game plan? Lydia, what's the game plan here to get A of 5? Okay, what would the height initial be? So the fourth interval is from 2.7 to 3.6. And this constant rate gives us a little bit of change in height, right? And so now I'm saying I want all the accumulated height from 0 up to 5. Whereas the fourth interval was just kind of like one slice of that, right? It was just like one part of that. So what's it going to take to get all the accumulated height from time 0 to time 5? Right? Right? How many is there? 1, 2, 3, 4, 5, and then part of 6, right? So it's going to take, we have to do this 5 times, right? And then do what? Because there's a little bit of accumulated height in the first interval. And then there's actually 0, but because it's 0 there. And there's accumulated height from that interval, and there's accumulated height from that interval, etc. So what do we have to do to get the total accumulated height? And then what are you going to do? Add them together, right? Accumulation. Yeah, the idea of accumulation is that it accumulates, right? Like running total, like it grows bit by bit. Yeah, so this is what we talked about. So you said we need to consider all the changes in height accumulated within each complete. This is key language here. Key language. Remember this. Completed intervals. How many completed intervals at t equals 5? There are 5. Okay, and it's not because t equals 5. Okay, it's just because that's how many completed intervals there are before t equals 5. Right? If we had picked delta t of 0.4, there'd be a lot more than 5, right? And then there's the current delta t interval. And what's dt in that interval? Yeah, it's 0.5. It's not 0.9 because we're only partially through that interval. Okay? So how do we... So those are completed intervals. Right? And that's the current interval. Important language here, so try to remember that. Full intervals that have already gone by, that have already seen their full accumulation for each of those intervals, we're going to call those completed intervals. And then there's a current interval. That's where the current value of t is. So here's the accumulation for the 5 completed intervals. Is this what you got? Right? Accumulation, adding bit by bit. It accumulates, it grows, running total, right? Running total. So we're going to add up all the accumulation from the first interval. And then we're going to add all the accumulation from the second completed interval. Then we're going to add all the accumulation from the third completed interval. And then the fourth, and then the fifth. And then will that give me A of 5?
Although you still have to, like, you still got to go with the current.
Right. And so what will that be?
4.5 to the 1.3 times 0.5.
Very good. Right. So then now the rate in that last interval is 4.5 to the 1.3 times the change, which is less because we haven't made it all the way through there. So given each of these rates, in each interval, we can calculate how much change, right? These are dh for each interval. And then for the current interval. And what will we do now to get A of 5? Add what? All that and that. We're going to add all that together. And what's the underlying principle here to get this accumulation of height? Constant rate of change. Each one of these is simply a, each one of these calculations is MDT. MDT, right? Constant rate of change for that duration. Gives a little bit of change. And then we're going to add up all the changes to get the total change. Super important because this is how the one-line accumulation function is going to work. It's just going to do this. It's just going to do this. It's going to go to the first interval, and it's going to do rate times the width of that interval. And that's going to go to the next interval. It's going to do width times that interval. It's going to go to the next interval and do the rate times that interval. And then wherever it is in the current interval, it's going to take the partial interval and do that constant rate times whatever duration you have or interval you have in that current interval. So this complicated one-line rate function just boils down to this. And I gotta keep that in mind. Because you could do this calculation for any t value, right? So if I had it, if I had t equals 2, it's unfortunate that all of them are that many intervals. Okay, anyway, so you see that you could do this calculation for any t value here, right? You just figure out how many completed intervals you have, calculate the dh in all your completed intervals, and then the little remaining dh in the current interval. You add it all up, and you get the total accumulated height at that t value. This is what our one-line function is going to do. All right, so let's get to it here. Let's move a little further forward. Any questions? All right, so let's just look briefly at this. Let's get our notation down. I don't like how chunky it is, but oh well, we're stuck with it. This one doesn't move smoothly. It should, but it doesn't. Okay, so can you, so we have our language down. Every single question mark is either a variable or a parameter, and the double question marks are like phrases or functions, okay? So quickly, can we identify all the things here, all the single question marks and double question marks? Get a partner, talk at your table. So brains are moving, voices are moving. Don't spin our wheels here. Okay, so you guys are making progress here, so let's go through them. The black, let's see, this one here. So I don't know if we mentioned this yet, but this is, well, you guys should know this from Calc 2. What is this? This is A, right? So A is the value of x at which we're going to start accumulating. So it's a parameter. It's a value of x. Oh, it's spinning. Don't crash on me. All right, it's the value of x that's going to be this, where we're going to start accumulating from. Okay, what about the black question mark down here? It's not total. Total you think of as the y coordinate, right? It's just x. It's the current value of x. It's the current value of x, or just x. Okay? Next is the blue. Blue question mark. Jason, all semester, everything we've done in 271. What varies through the intervals? What varies through intervals? It's a variable. Delta x is not a variable. Delta x is a parameter. It's our interval width that we set. And then what varies through delta x intervals? dx varies through delta. It's a variable. dx varies through. Okay, so what's the purple one? No, so then that's our delta x intervals. That's our parameter. dx varies along with the current value of x. It varies. So what is the range of dx? It varies from what to what? Zero to delta x, right? The beginning of the interval, dx is 0, right? Now dx is 0, and then it varies until it reaches
The full length of the delta.
right. So it varies from 0 to delta x in every interval. Okay, what about what's next? I don't think so. I think the purple double is next. So what are the purple double? Okay, let's completed intervals. Completed intervals. What about the double gold arrow or question mark? It's the current interval. Jumping down on me. Why do you do that? Stop moving. All right, there we go. All right. Oh, jeez. What is the red question mark?
That's like the exact rate.
It's not a rate. It's an x coordinate, right?
Oh, okay.
So what is the red question mark?
Isn't it your
We'll
final?
just explain it. So like,
Oh,
explain what it is. What is? You don't have to have the notation perfect, but what is it doing? What is the red question mark about? Is it a rate?
the starting value of
So yes, it's the beginning of an interval, but you see it's not a rate because rates are, where do you look for rates on this graph? Sorry, single red question mark. The single red question mark. The x value, that? No, it's about the current interval, right? So that the red question mark is about the current interval. It's the x value, it's not the start of dx, because dx goes from 0 to delta x.
Or it's where dx.
Now this is going to have coordinates that are like x, right? This is x coordinates like x. So it's the x value at the beginning of the current interval. It's the x value at the beginning of the current interval, and we call that's called left x. We'll talk about that next time. That's left x. All right, what about the double red question mark?
Exact.
Exact rate, and the black, double black? Approximate rate r, right? So r sub f, and then just r. Okay.